We're going to look at an integration technique called substitution. But before we do that, let's review a few things that will help us with that method. First of all, we had some basic integration formulas. We had an integration formula that would help us integrate something to a power. We had an integration formula for e to a power. And we had an integration for 1 over, we used x, in this case it's u, which integrated to the natural log of u. So what I'd like you to notice about these formulas is that they're the exact formulas we've used before. The only difference in the way these are written is that instead of the variable being x, we're writing this with a variable of u. Now that makes absolutely no difference to the formulas, but it's going to tie into what we do when we integrate by substitution. The other thing that I want to review is the whole meaning behind differentiation as a rate of change. So let's use this as an example. So let's say we had the function y equals x to the third, and we want to find dy. We want to find the change in y. So if we take the derivative of y with respect to x, that derivative will be 3x squared. But if we want to find the change in y, dy, we could take both sides of that equation and multiply both sides by dx. Multiply both sides of the equation by the change in x. And we'll see that dy, the change in y, is 3x squared times dx. Now you might remember that when we wrote integrals, we always had this dx in the integral, and that was where the dx came from. It came from the fact that a derivative was a change in y with respect to the change in x. So now let's try this technique of integration called substitution in order to find this integral. This integral probably looks a lot more complicated than the ones that we've worked on before. We can take this integral and rewrite it as something that fits into one of our basic integration formulas, and we'll do that by making some substitutions. What we can notice is that our integral looks a lot like the integral of u to the r, because in both cases we have something raised to a power. In our case, it's x to the third plus 1 that's raised to a power. Just to make this a little more clear about what we're doing, let's move some of these factors around inside of our integral. So we'll just rearrange our integral so it looks like this. Now let's notice that in both our integral and the basic integration formula, we have something to a power. So the x to the third plus 1 is acting like the u. So we're going to write that down as a substitution equation. We're going to say u and x to the third plus 1 are equivalent to each other. Now that means that we could take the derivative of u with respect to x, and we would get the derivative of x to the third plus 1, which is 3x squared. If you look at our basic integration formula, you'll notice there's also a factor of du. So what we're going to do is take the du dx equals 3x squared, and we're going to multiply both sides by dx to solve for the du. So du equals 3x squared dx. So now how does that fit back into our original integral? Well, 3x squared dx is a factor in our original integral, and we've just said that du is equivalent to that. So we'll substitute du for the 3x squared dx. Now that we've substituted in our original integral, we've got something that we actually can integrate. This fits our basic integration formula. The integral of u to the 10th du we'll find by adding 1 to the power, so we'll have u to the 11th, and dividing by the new power, which is 11, plus our arbitrary constant of c. So we've been able to integrate because we made the substitution, which allowed us to use one of our basic integration formulas. Now the only problem is our original problem did not contain the variable u. It contained x. So we're going to have to back substitute for the u. Remember, u was equivalent to x to the third plus 1. So we'll replace the u with an x to the third plus 1. So now we've integrated and we are back to our original variable x. So let's try that same method of substitution on this integral. You'll notice that once again we've got something to a power. That's the 2x squared plus 3 to a power. So we're going to make a substitution for the 2x squared plus 3, and we'll call that u. Now if u is 2x squared plus 3, then the derivative of u is 4x dx. Now look back at the original problem. We had a 4x dx in the original integral. So now we'll be able to substitute for the 4x dx by calling it du. Which means we now can make a substitution for the 2x squared plus 3, that's u, it's to the third power, and a substitution for the 4x dx, that's du. So now we can integrate by adding 1 to the power and dividing by the new power, plus the arbitrary constant c. But remember, we have something that's in terms of our substitution variable. We need to get back to the original variable x. So we know that u is equivalent to 2x squared plus 3, which means we'll take the u out and substitute in a 2x squared plus 3. And we've got our final answer, 1/4 times 2x squared plus 3 to the 4th power plus c. Substitution works as an integration technique if we can make this integral fit into one of our basic integration formulas. So sometimes the trick is figuring out which basic integration formula we're going to be able to use. Now in this case, this is the basic integration formula we'll be able to use. And the hint here is that the derivative of the denominator, the derivative of 1 plus x squared, is something that we see in the numerator. The derivative of 1 plus x squared is 2x. So let's see how that works with substitution. The u and the 1 plus x squared are going to be equivalent to each other. So that's our substitution equation. If we take the derivative of u, the derivative of u is 2x dx. And that's exactly what we have in the numerator of our fraction. The 1 plus x squared will get replaced with a u, and the 2x dx will get replaced with a du. Now don't be fooled by this. The integral that you're looking at right now, du over u, is exactly the same as the integral of 1 over u du. So that means we can integrate, and the integral will be the natural log of u plus c. Now we'll back substitute. U is equivalent to 1 plus x squared. So when we substitute back in, we have the natural log of 1 plus x squared plus c. So what do you think the u is going to be in this problem? Well, maybe the clue is coming from the fact that we don't have a basic integration formula that tells us how to integrate the natural log of something. That's probably what we need to substitute for. If we let the u be the natural log of 3x, then the derivative of that u is 1 over x. So the derivative of natural log of 3x is 1 over 3x times 3, which is just 1 over x dx. So now let's see if we've got those pieces inside our integral. u is the same thing as the natural log of 3x. So we've got that piece. And du is the same thing as 1 over x dx. And that's exactly what this is. Dx over x is the same thing as 1 over x dx. So when we substitute, the natural log of 3x becomes a u. Dx over x becomes du. So now when we integrate, we'll add 1 to the power and divide by the new power, plus c. And then we'll replace the u with the natural log of 3x, since those were equivalent. So the integral of the natural log of 3x dx over x is the natural log of 3x squared over 2 plus c. Now what probably stands out in this one is that we have e to a power. And we certainly know that we have an integration formula for e to a power. So let's make the substitution for the exponent. So let's say that u is going to replace the x squared. Well, so far, we would have the integral of e to the u then. But we still have to substitute for x dx. So let's go back to our substitution equation, u equals x squared, and take the derivative of both sides. And we see that du is 2x dx. And that's almost what we need. We need a substitution for x dx, not 2x dx. But that's not a problem. We'll take that equation, du equals 2x dx, and just multiply both sides by 1/2. So 1/2 du is x dx. So now the x dx gets replaced with 1/2 du. Now 1/2 is just a constant that's multiplying the function, so we can go ahead and bring it outside the integral. And when we integrate e to the u, we still have e to the u. So our integral becomes 1/2 e to the u plus c. But now we have to back substitute. U has to get replaced with x squared. And we finally have 1/2 e to the x squared plus c. So let's look at one last problem. This one is not an indefinite integral, it's a definite integral. We've got limits of integration from 0 to 1. So we know that that means we need to integrate, and then we need to evaluate by substituting 1 and 0 in place of our x's and then subtracting those. So we will end up with just a number, which we've said we can think of as area under a curve. But before we get to that point, we have to integrate. So our substitution will be for the 3x squared minus 1. That will be our u. The derivative of that is 6x dx. So let's see if we've got all those pieces inside our integral. We certainly see a 3x squared minus 1. That will become u. And the 6x dx becomes du. So this looks good. We can substitute for everything. So we have the integral of u to the third du. Now here's one really important thing. This is a definite integral. We do have an upper bound and a lower bound. But do you notice that when we substituted, we don't have those limits of integration written. We don't have the 1, we don't have the 0. And that's because the 1 and the 0 are lower bounds and upper bounds in terms of x. We now have an integral that's in terms of u. So those bounds have changed, and we can't say that we're integrating from 0 to 1 anymore. But that's okay. We can leave those bounds off, and we'll bring them back in once we back substitute. So let's go ahead and do the integration. So the integral of u to the third is u to the fourth over 4. Now, if it's an indefinite integral, yes, we would have a plus c, but remember, what we're going to do is back substitute, so we'll have our variable x back again, and then we'll be able to evaluate. So we're not going to worry about the plus c. But we do want to go back to our original variable. So we'll substitute 3x squared minus 1 for the u, And now that we're back to our original variable x, we can evaluate at our original limits of integration from 0 to 1. So we'll substitute a 1 for our x and a 0 for our x, and then subtract. And we have a final value of 15/4. So the important things to remember about substitution are that the reason we do it is to make our integral fit one of our basic integration formulas. And when we do it, we have to substitute for everything we see inside the integral. So in this case, we had to substitute for the 3x squared minus 1. We also had to substitute for the 6x dx. So make sure that you're substituting completely, and make sure that in the end you back substitute to get back to your original variable.